All right, so this is Robert speaking from lockdown but sunny Berlin. Welcome everyone to today's webinar. So we'll be talking entirely about Gurobipy. I guess most of you have encountered that interface before, or maybe you're a regular user already. So Gurobipy is our Python interface to our C library, and mostly is constituted from lightweight modeling objects and thin bridges to the C library. There's not too much going on in that interface itself. It's designed to not put a big burden on things. What we do, however, we take advantage of the flexibility that the Python language offers. So we overload certain operators or use, or one could say abuse, rich comparisons, and just that you get an idea, if you haven't met Gurobipy before, this is the smallest, at least mildly useful Gurobipy program you could possibly write. So let me check if I can get a pointer here. Yeah, there it is. So how do you start any Gurobipy code? You import the package. The convention I use is I just use GP as the qualified name for the import. But you create an optimization model. This acts as the main data structure you're going to interact with. For example, you can use this model reference to add an optimization variable here. And then another useful method is adding constraints. So you can add a constraint X must be at least 42. So that's pretty neat and useful already. If you want to run the numerous examples I have on my slides here are the quick start installation instructions. You need to have Python installed on your computer. Then you navigate to your Gurobi installation directory. And if you've set up Gurobi in the usual procedure, you should already have an environment variable or something alike that points to that directory. And inside that directory, you will find a script, setup.py, and you just call it with the installer command. And then, since this is about matrices, please be sure to have installed both Numpy and Scipy. And the easiest way to get this is just to call pip. So why are we doing this webinar today? So one thing that you know if you're engaged in the numerous numerical computing communities that Python have, maybe you use scikit-learn at some point, or maybe you use pandas a lot, that no matter which numerical computing package you use, you will always be confronted with NumPy's ndarrays. So an ndarray is a multidimensional array for dense data, and it's written for efficiency and for generality, and it's used everywhere. And another thing, especially for us, that we are working in operations research and numerical optimization, is sparse matrices, because many of our optimization problems are naturally sparse. You have a road from one town to another, but you don't have every road between all the towns, so you have naturally some sparsity there. And for Gurobi version 9, we have done something that I wanted to see a long time. It's an integration of expressing matricial data into optimization models in Gurobipy. So this will be driven by examples a lot, and if you run these examples, please be sure to have the imports ready here as I have in these 3 lines. I don't reproduce them in every example because they just take away too much space. Now, I've been talking about matrix friendliness and using matrix data to express optimization models. So just a contrasting term, so what is our current Gurobipy approach? I think a good terminus for that is term-based modeling. Let's do one concrete example how you typically write a Gurobipy model. Okay, you create a model, gp.model, code constructor, get the reference. Let's add 3 optimization variables, x, y, and z. Each having upper bound 0 and the lower bound 0. It's implied because that's the default for optimization variables in Gurobipy. And then you can do the following. You can say, okay, my objective function should be x times x plus 2 times y plus 3 times z squared. So you see, we have expressed our objective function in algebraic terms using operations like multiplication and addition. And this is what I refer to as term-based modeling in this webinar. And of course, the same works for adding constraints. So here you have m.add constraint, x plus 2y plus 3z greater or equal than 4 and another constraint. So that's pretty natural. You can express it exactly as you would write it in paper. And if you're used to think in terms, this is the right approach to follow in Gurobipy. However, if you are used to think and express optimization models in matrix terms, this is somewhat not the right approach to code. So let's look at this general form of a quadratic optimization model. And this is what you find in any textbook on operations research or numerical optimization. It's not phrased in x plus z plus y. It's phrased in matrices and operations of data expressed as a matrix and a vector of optimization variables. Similarly, here, the objective function, it's not a sum of square terms or mixed terms or whatever. It's expressed as a quadratic form. So this is the matrix representation of it. And x transpose from the left multiplied and x from the right. This gives you a function. Now, if we were forced to squeeze this into a term-based modeling approach, what would we need to do? We would need to look at all the non-zeros of Q and A, patch the coefficients, and build expressions for the individual constraints or for the resulting quadratic form in expanded form. Now, of course, this is possible. You can do it. It's not that complicated, but it's not really satisfying because you already have the mechanics of the expressions expressed at a much higher syntactical level. It's already given by the algebraic properties of the matrix vector product or this product here. So this is what we added in Gurobipy version 9. You can now phrase such models directly in terms of matrices and vectors. So and if all this is really alien to you, so here's just two concrete examples that I always have on my mind when I think about modeling optimization models in matricial terms. The first is maybe you're doing some network flow optimization and you already have your road network or whatever network you have in some kind of graph. Now, it's easy to define from the graph a node arc incidence matrix, and most of the graph algorithm packages have this built in more or less. So instead of looking at each node and arranging the terms so that the sum of the incoming flow edges minus the sum of the outflowing edges must be equal to the node balance, this would be the term-based thinking, you can just say, oh yeah, but A is the node arc incidence matrix, so flow conservation is just given by A times X equal to F, the balance vector. Or another example, if you're doing some sort of portfolio optimization where Q is a covariance matrix or an estimate thereof, then of course, you know how to interpret the quantity X transpose QX, that's just the variance. And why go back and sum up individual terms if that already expresses the gist of your model? So let's do one simple but concrete example. So this is on the left now, the simple optimization model in term language that we have seen before. So the three variables x, y, z, the objective function, quadratic, and two linear constraints. Now let me rewrite this in terms of matrix data. Let's look at the top three lines here first. So the objective function is x squared plus 2y squared plus 3z squared. So as a matrix representation, it means we're just having a diagonal matrix with the values 1, 2, and 3, 1, 2, and 3 on the diagonal. Now let's look at the linear constraints. The coefficients, if I read it row-wise, are 1, 2, 3, first row, and 1, 1, and nothing for z, which makes 0 for the second constraint. So that's exactly what the A is about. First row 1, 2, 3, second 1, 1, 0. And then there's the right-hand side for the linear constraints, 4 and 1. Well, that's exactly here this array. And so now, assuming that we have given the data in matrix form as we have now, let's go set up our optimization model, gp.model. And then now comes the first thing that is new in version 9. We have added a function to the model class, add MVar. So the MVar is an acronym for matrix variable. And so the first argument, in the sense that how many variables should this matrix variable comprise? So here it's 3, because well, my model in X, Y, and Z, we have 3 variables. And all of them should have the upper bound of 1. And now everything is just really canonical. What is the objective function? It's just X, matrix multiplication, cube, matrix multiplication, X. And what is the constraint? Well, it's A times X greater or equal than B. So it's as easy as this. The MVar object is probably the most important one if you want to work with matrix data. So let's spend some time on understanding exactly how to create them. An MVar is it's one single object what you get, and it represents a vector or a matrix. I mean, any vector can be interpreted as a matrix of optimization variables. And you don't want to construct these objects from any constructor, but instead you always go to the factory function model.add MVar. Now here's the signature of that method. The first argument, this is like the crucial one. It's the shape argument. And now if you've worked with Numpy in the past, this should be really canonical for you, because this is just the same kind of shape that is omnipresent in the Numpy world. So it gives you the dimensions of the matrix variable. And the rest, we have a couple of keyword arguments: lower bound, upper bound, objective coefficient, v type, the variable type. These are exactly of the same form as for the existing method model.add_var and model.add_vars. And now you can pass for any of these parameters. For the keyword arguments, you can pass either a scalar, done here. In that case, that scalar is broadcast to all the variables that are in this matrix variable, or you can give any iterable that has as many elements as the total number of variables, so the product of the dimensions of the shape. And we will read it off from there in canonical C order. So it's pretty much like in Numpy. Let's go through some concrete example that was a little bit dry. So let's look at some simple stuff here. What does this do? Model.add_var, and now here's the shape. The shape is 4, 2. So we see this is a matrix variable with 2 dimensions, and the length is 2 in the last and 4 in the first. So if you think of a matrix, it should be 4 rows and 2 columns. And for all of these variables, we have the constraint that they are binaries. Now what's this? We add an MVar, and now the first argument, this always looks a bit funny, but this is just the way you write a one-element tuple in Python. So it's a matrix variable having 1 dimension, so it's a vector, and has length 3. The lower bounds for the individual variables is -1, -2, -1, and the rest is tied to default. So next example. Now we do away with this funny single element tuple. If your matrix variable is 1D, then you can just pass in a scalar integer, and we will interpret this as a one-dimensional. This is just for convenience. Same here, lower bound hasn't changed. But of course, you can go fancy here, and there's no restriction on the shape. You can create a 4-dimensional 8 by 8 by 8 by 8 variable. So this is in total 4096 optimization variables in one MVar. Great. Now we know how to construct the MVars. Next thing, what are the operations we can do with it? Let's look at our code setup. We have an optimization model, and I disable output so that the output that is produced doesn't clutter up the slide. We add 1 variable x of shape 2, 3, so 2 rows, 3 columns. The upper bounds of this total of 6, so 2 times 3 variables, range from 0 to 5, and all have an objective coefficient of 1. And then here I do a trading model.update. This is just for convenience so that I can query the values we've set later on. So what do we have here? This is the first very important operation. It's a matrix variable. It inherits the slicing properties of ndarrays. So any slice you can apply to an array, you can apply it here as well. So for example, this would say, please give me the submatrix consisting of the second row and the second to third column of the MVar. So this is again an MVar of dimension 1 and length 2. Next thing, you can query all Gurobi attributes, so all variable attributes, on MVars directly. And what you get back are appropriately shaped ndarrays that hold the data for all of the matrix variable. So here we said the upper bound ranges from 0 to 5, and that's what we see exactly here, C order. You not only can query attributes, but you can also set them. And to be a bit more fancy, you can set them directly on the slides, as you would expect from NumPy-like syntax. So here we modify the objective coefficient of the variables in the third column. And we do this via a scalar. So this is then broadcast along this dimension here. Okay, and then because we're a bit paranoid, we better check that this update of the objective coefficients has actually arrived. So let's update the model and print, as we did here for the upper bound, the corresponding objective coefficients. And as expected, in the third column, we now have -1 instead of the initially set +1. Of course, now you can solve. We have actually now a trivial but non-empty optimization problem to solve. So why not solve it and query the solution? And as for the upper bound or any other variable attribute, you get the solution now in form of one ndarray. And it looks kind of correct. So by default, we have a minimization problem. And the objective coefficients for these two guys is negative, the other is positive. So these are set to 0. This is good. And these are sitting at the upper bound. So this looks correct. Very good. So we have seen how to construct MVars, how to play with them. And now we will see how to use them to build linear expressions with them. And all of these expressions, you've seen it from the examples before, they are just created from applying the matrix multiplication operator to it. So what is the typical use pattern I have in mind, and that probably most of the codes will follow in the end? It's you pass into the add constraint method of a model expressions like this: a times x equal to b. Now the a, this is the data, and what we accept here as data is either a numpy ndarray or a scipy.sparse matrix. And of course, by the requirements of the multiplication operator, the shapes of a and x must be compatible for matrix multiplication, so as the right-hand side in the end. The right-hand side b, we always assume it is a numpy ndarray or a scalar. And of course, sense-wise, this invokes just the Python-rich comparison. You can use either equality or inequalities here. Let's do one quick but simple example that solves a sparse linear system. So let's acquire some data to play with. Let's get a random sparse matrix from the scipy.sparse package, having 8 rows, 128 columns, and average density of 20%. Here's the compatible right-hand side. So B, it's a random dense vector of length 8. And now it's as easy as written here. You just get the optimization model constructed, add one optimization variable of length 128. And all we need now for the linear system to be added, it's a times x equal to b. That's it. Of course, this was just one example. Let's look at a few more examples to get a better feeling what we can do with these expressions. Here again, some data to play with. We have one matrix, a random dense matrix of shape 5, 3, another one of 5, 10. Let's define again optimization model. gp.model gives us that. Add one optimization variable of length 3. This kind of looks correct because we have 3 columns in A sitting here. And now let's add a constraint a times x equal to 1. So what is to note from this? If you pass in a scalar, right-hand side will broadcast this in the missing dimension. So this will be equivalent to writing a times x is equal to the all ones vector of length 5. Next example. Let's add another matrix variable y of length 5. And now we add a constraint that says y must be equal to the matrix vector product of a and x. Very nice. So this is a way to chain matrix operations in a way. And then there's, just to feature it, a convenience function that is often, that at least I need often for modeling. You can just write for an MVar, MVar.sum, and this will give you a linear expression that represents the sum of all the entries of the optimization variable you've invoked this method on. And we say it must be at most a half. And of course, now these compounds, so these matrix times vector terms, they can again be used to compose expressions. As on the scalar level, you could write x plus y. You can add the resulting linear expressions from a times x here with d times z. And matrix thinking, this gives you concatenate in a way a and d along the second dimension and stack up x and z, and this gives you then another matrix. Okay, so you can work with these individual terms, matrix terms, simply by adding them up or multiplying them. So there's one caveat though that I need to mention at this point. We have seen that the MVar objects are essentially n-dimensional. The linear constraints, however, we have a restriction currently that constrains them to be one-dimensional. So here's one concrete example that does not work yet. Assume you have some matrix A of shape 4 by 4, another one B also 4 by 4, and an optimization variable also of shape 4 by 4. Now, algebraically, the constraint AX equal B, this is nothing else but 16 linear constraints. And it kind of would be nice if we could phrase them directly like this, but this didn't make it in for 9.0. You have to always constrain the constraints you're adding to one dimension. And typically an efficient way of doing that without creating too much messed up syntax is just using a generator expression like this. Here we slice 4 by 4 linear constraint in the trailing dimension. So we use a variable j that we range over 0 to 3 and add 4 by 1 constraints instead of adding 1 4 by 4 constraint. So this is mathematically, of course, exactly the same. It's just a bit more clunky to write down. Okay, I think we're done with the linear part. Now let's look about quadratic expressions and functions arising from quadratic expressions. And it's best explained directly by example. You would have guessed it. Of course, we just used the matrix multiplication operator to bring them to life. So what are concrete examples? Let's start with, again, this optimization model. Let's add one optimization variable of length 3. And now what does this do? Well, x times x, well, this is just the inner product of x and x. So it's just x0 squared plus x1 squared plus x2 squared. This is quite natural. Another example, assume you have some random matrix F here. So maybe you interpret this maybe like a time series of 10 assets. Here's an optimization variable, your investment vector. You build the covariance matrix F transpose times F. Results, we save it to sigma. Well, and then to minimize the variance, all you need to do is to say that objective y times sigma times y. Of course, all these quadratic expressions, they have nothing to do with the objective. It's just where you put them in the end. You can use all these construction magic to add constraints, of course. So let's do one example here from this as well. Let's add one variable s, length 100, another variable z of length 100, and add the constraint s times z equals to 0. Now let's think about it. What does it mean? Well, the variables s and z, they have a default lower bound of 0. And what does this constraint do? Say it says the inner product of s and z must be 0. So the inner product of s and z is the sum of the terms si, zi must be equal to 0. Now, since each of the terms involved are non-negative because the operands are non-negative, it just says all the products si, zi must be 0. So this is one way to, for example, express a complementarity constraint here. Now, this syntactic convenience, this is certainly very nice, but it was also a design goal to avoid any I shouldn't say any, but most of the Python overhead from creating intermediate Python objects. So let's look again at the two versions of that simplistic example I gave in the beginning. What happens here in this line? Let's dissect it with the eyes of Python. So x is an optimization variable here. If I write x times x, this will lead the Python interpreter to call the multiplication method of the var object x with the operand x. And now the logic of the result is implemented in this var object. So this will create another Python object, which is returned. This goes on for this term as well. And then there's the plus. So we have a result for this, in Python object for this product here. This will be invoked for the plus operator, giving the argument here. And the result will be yet another Python object. And one more round, we call then the plus operator on this compound expression object with the argument of this. So, and yet another object will be created. So you see, it's natural to write down linear expressions like this, but it invokes Python machinery. And usually you won't see it, but you will see it if there's a huge number of such operations happening on the Python virtual machine. And we do not want to reproduce this overhead if we have already given the linear expressions on the higher matrix level. Let's look at our example in matrix data here. And the beauty of having this expression x times q times x is we will invoke the method matrix multiply from this object. It will get as input this. But now we do not need to invoke Python methods or objects for all of the non-zeros of Q. We just have to work with Python operations proportional to the number of total terms in this expression. So the non-zeros fall completely out of the picture. So this will be for free essentially, because that's just one term. Same here, a times x, all this will do is it will save away the A matrix, which is given in either Numpy data structures or Scipy sparse data structures. And these are C-level data structures. And what we will do in the end, we will directly copy on the C level the data of A to our internal data structures in the C library. So there's very, very little overhead. And actually, you see it. So here's one example that I want to run through with you that underlines this a little bit. So let's go back to our random sparse linear system, but let's crank up the dimension a little bit. So now we do it for 1024 rows, 8192 variables, and again, density 20%. We just generate a sparse matrix, random, and a compatible sized right-hand side vector. And this was the optimization model you would have to write down using an MVar. Now I sat down and tried hard to come up with the most efficient way to write this optimization models without MVars. And this is what I at least came up with. Maybe you have a better idea how to do this faster, but this is just the best I could come up with in reasonable time. What do I need to do here? I need to create not an MVar, but I need to create a list of n variables that I will use for composing the terms of the linear constraint. This is what this line does. And then what I will do, I will loop over the rows of A, extract for each row the coefficients and column indices of the coefficients. And then I will just compose a linear expression object, which is part of the Gurobipy package, by just passing in the lists of the coefficients and the corresponding variable. And once I have the linear expression, I will just add the constraint, this linear expression must be equal to the right-hand side for this row. And finally, just as a reference, if I wouldn't think hard about it, how to do it efficiently, this is what I would do on the first try. I would just go get all the non-zeros from my matrix A. This is what this line does. I would create, again, n variables to form the expressions. I would prepare for each row of A an empty linear expression. And then I would simply loop over all the non-zeros of the constraint matrix A and add the appropriate terms, so the coefficient times variable, to the corresponding linear expression for this row. So once I've eaten up all the terms for the linear expressions, I will just finalize this by ranging over the linear expressions and adding linear constraints for each of them. So this is exactly the same part, the same line as here. Okay, so now I would be a really bad storyteller if the MVar approach wouldn't be the fastest. Of course, this is the case. So this is roughly a factor 20 faster than the best term-based approach I could come up with. And here now, this 53 seconds, here you really see the effect of having a huge number of elementary Python operations going on. So this loop here, we loop over the number of non-ndarrays. This is really a long loop, and there's no just-in-time compilation going on in CPython. You just have to do it on the Python level. And this is why this is slow. And now, what is the message here? I think there are two messages that are interesting. One is, if your data is naturally expressed in matrices and vectors, you can expect good performance by expressing it directly as such in the constraints and functions, objective functions. If your data is naturally expressed in terms, and maybe you have some random values in some database and you don't have the global picture of a matrix, you make sure that you reduce the number of elementary Python operations if possible. And often it is possible by by collecting terms somehow and passing it more in bulk into Python function. And what a not message is here is you don't need to rewrite your term-based optimization model with matrices for performance. This is a huge problem here in terms of non-zeros, right? This is still very fast. And then there's one more technical slide. Maybe this is very specialized, but I want to show it nevertheless. We have seen that we can create these matrix expressions with the matrix multiplication operator. And as you know, this was only introduced in Python 3. So all the examples that I've just shown to you, you cannot use them with Python 2. For this, mostly for this case, maybe there are a few more, we also have some lower level API functions in Gurobipy, where you can add constraints, quadratic constraints, and objectives also in terms of matrices, A, Q, Q, C, this is linear functions. So this also gives you an opportunity to pass in the data in bulk in matrix form, even though you're tied to Python 2. And there's literally no overhead here. So this should be as fast as the other approaches with matrix data. All right, so let's wrap up. I think the message I wanted to bring to you is, if your optimization data is naturally expressed in matrices, well, embrace this structure and reuse it for your Gurobi optimization models. And while I'm excited that we can now do this, you could do so much more. I could think of numerous things that we could potentially add and make it easier and even better, but there's just too many possibilities. So if you have one or two specific things that you really miss, of course, let us know. We have a user forum in our support page where you can post things, or if you're a maintenance contract, why not post a support ticket with feature requests and explaining a little bit why and how you will use this. And this concludes my talk. Thank you for attending.